Hi everyone, welcome to this webinar. It is RSWall webinar series part 3. It's about the unique applications of MSE walls and gravity lock block walls in construction. Today, we have a guest from a Kuwait company, Ali El Matarawi. He's gonna present in this webinar, thank you for helping me out, Ali. My name is Sina Javankhoshdel. I'm the senior manager of the limit equilibrium team at Rock Science, and I manage slide 2, slide 3, and RSWall products. About Rock Science, Rock Science is the world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical engineers. We are dedicated to deliver high-quality products and exceptional customer service and technical expertise. And from a team of 25 years ago, we have grown to a team more than 80 people. So, and we have over 10,000 customers around the world. These are our products. Now we have 20 products. Last week we released our 20th product, which is RS Seismic. And if you want to know more about it, you can go to Rock Science's website. And this is the Rock Science ecosystem, software ecosystem. Since they are all developed in-house, they have the capability of being integrated with each other. And today I'm going to talk about 2 of these products that they are integrated, which are RSWall, which is for retaining wall analysis and design, and slide 2, which is a 2D limit equilibrium analysis for slopes. Before I pass the presentation to Ali, there is just a quick video about the features that we have in RSWall. And then after that, I will pass the presentation to Ali. This is RSWall. We have different types of walls: MSE, gravity, cantilever, gabion, abutment, block walls, and wraparound walls. Different wall types. We cover different standards: AASHTO, FHWA, NCMA, Australian, British standard, and Eurocode, and user-defined standard. We consider different failure modes in RSWall, including external, internal, and reinforcement strength. So these are different failure types that we have in RSWall. We have different methods to calculate active pressure and tension reinforcement and passive pressure. You can model single segment MSE walls in RSWall, and also you can do multi-segment wall using the multi-segment wizard that we have. And this is an example of multi-segment walls with the 3D view. You can do uniform and non-uniform block walls using RSWall. You can model gravity walls, cantilever walls. As you can see, they have different shapes and you can create them. Gabion walls as well. And abutments. We can have constant focus load on the abutments as well. We have manufactured libraries for geosynthetics and blocks, facing blocks of the wall. And we have different load types, live loads, permanent surcharge loads, and they can be applied vertical and horizontal directions. And we have different shapes for back slope and front face as well, and also uniform and non-uniform support configurations. You can add them to the RSWall program. And in terms of results, we have a detailed presentation of the results, including the detailed hand calculation, which we're going to see in today's webinar as well. And something that we're going to talk about today is the seamless integration with the slide program. And at the end, you can export your different parts of your model, including profile and topography, to the Excel files as well. So let's move on to the next section, which is part of the focus of this presentation today. We're going to talk about MSE walls in construction, and I will pass the presentation to Ali to talk about this part of the design.
All right. Well, thank you very much for this introduction. As Sina mentioned, my name is Ali, and I'm a geotechnical engineer with Kiewit, and my focus is on design of temporary structures. And so today, I'll predominantly be talking about how retaining walls fit in the context of temporary structures used during construction and how they can be cost-efficient solutions. My main focus will be on presenting two case studies. One for an MSE wall that was designed to support a self-propelled modular transporter. Throughout this presentation, I'll be referring to it as SPMT for short. And then the second one will be on a log block wall that was constructed over sensitive clays. But just before we go into all of this, very briefly, for those of you who may not know Kiewit, it is one of the largest construction companies in North America with offices across both US, Canada, and Mexico. And it's been ranked in ENR's top 10 contractors since 1995, with last year being ranked as second overall and ranking first in a few other categories. So, like I just mentioned, retaining walls can often be used as temporary structures during construction. Examples can be if you need to steepen an existing embankment to permit construction adjacent to it, or if you need a shoring wall to allow construction of an underground parking structure for a high-rise building, or if you need to temporarily widen the road on an embankment where your right-of-way is limited. And so, depending on the application, you may be limited to a wall that uses either a top-down construction approach or a bottom-up. So a top-down would be, as you can imagine, you excavate benches and you install your support as you go down, whereas a bottom-up, you're typically backfilling as you build your way up. So examples of top-down walls, like I just mentioned, would be, for example, soldier pile and lagging, so shoring type walls. And that's shown in the top left photo, or soil nail walls, which I'm showing in the top right. On the flip side, examples of retaining structures that we built with bottom-up construction approaches would be MSE walls, like I'm showing in the bottom left, or log block walls in the bottom right. But generally speaking, though, bottom-up type walls are more cost-efficient options. However, they normally require more space in order to construct it, and so they're not always the most feasible option. And today, I'll actually be focusing on primarily MSE walls and log block walls. So let's just jump right into it. The first case study here is for an MSE wall that was constructed to permit the movement of an SPMT during a rapid bridge replacement. I'll show what an SPMT looks like, but for those of you who may not be familiar with it, that, like I mentioned, it stands for Self-Propelled Modular Transporter. And you can think of it as an oversized heavy-duty flatbed that is used to transport incredibly heavy objects, and in this particular case, 2 bridge structures. So this was for the Highway 417 Midtown Rapid Bridge Replacement Project, which was in the city of Ottawa. And the scope that we had here was to demolish and rebuild 5 bridges using the RSWall approach. But the one that I'll be focusing on today is the one over Preston Street. And here are 2 photos of what the bridge used to look like. That's in the top photo, and then the new bridge right after it was moved in, which is in the bottom photo. And so just very briefly, the RBR sequence here was to build the new bridge structures within a casting yard. Typically, that's done near the final bridge location. And normally it's done a year or so before it has to be moved into place. And a few days before the move, the travel path of the SPMT is prepared, which in our particular case consisted of doing some subgrade preparation, protection of buried utilities, and so on. And during a weekend, the highway is closed and the existing bridge is demoed. The new bridges are moved into place with the SPMTs. Backfill is immediately placed behind the bridge abutments, and the highway is reinstated and opened before the start of the work week. And so, as you can imagine, this is a very schedule-driven operation with really no room for error. But to better understand kind of where the context of the MSE wall fits into all of this, we'll talk briefly about the SPMT. So its width from one edge of tire to the other edge of tire is approximately 12.4 meters, and it has a total length of 25.9, and it's supported on 288 tires. So like I mentioned, it's a massive vehicle. The two bridges that we actually had to move into place, each one weighed about 2 million kilograms or 2,000 metric tons. So these are the kinds of structures you would normally use for an SPMT of this size. And so obviously of key importance to us when you're designing an MSE wall is your surcharge loads. And so in this case, the SPMT pressure under its entire footprint was about 105 kPa. So again, very, very large loads. Now, where does the MSE wall fit into all of this? So the new bridge, which was being moved into place, I'm showing here by the pink shape, would have been supported on the old bridge footings shown by the green boxes, and partly also on the newly constructed thrust block, which I'm showing by the blue boxes. And so the SPMT, as it travels along, it needed an elevated grade, which is what I'm showing by the thick yellow line. And so you can immediately see that there is a bit of an elevation difference that had to be made for between the top of the travel path and where the footing would ultimately rest. And because there really was no room for cut slopes, which would have been the most economical option in this case, the second most economical option was MSE walls, which we built on both sides of Preston Street, and I'm showing here by the green boxes.
Yeah.
And so just even looking at the picture, you can already see how things are quite tight. So with the SPMT being around 12.4 meters wide and the travel path being 14.8, this really only left us with 1.2 meters of clearance on either side of the SPMT. So that's the measurement between the edge of the SPMT tire and the front face of the MSE walls. So already very, very tight conditions. But in reality, the actual offset that we ended up having between the edge of tire and the front face of the MSE wall, based on a predefined travel envelope for the SPMT, I'm showing here by the green shapes or the green lines, was only 0.8 meters. So this obviously made the design of the MSE wall even more challenging. And so if we take a quick look at the MSE wall, it was designed by the supplier and it was built by Kiewit. But because, like I mentioned, it's a very high risk operation where really there was no room for error because of schedule purposes, a peer review was done by Kiewit's in-house engineering department. And so the MSE wall consisted of wire face baskets, and it had struts every 0.3 to 0.5 meters. And the geogrid in this case were Pyramid 70 uniaxial geogrid, which had an ultimate tensile strength of 70 kilonewton per meter. And the length of the walls between one side and the other ranged approximately between 55 meters and 59 meters, and were a total of 4 baskets high at its highest points, and that is equivalent to 1.82 meters. And I'm showing photos here of the east wall, which is in the top, and the west wall, which is in the bottom. But today's focus will primarily be on the west wall. And so you can obviously imagine that there were some technical challenges that we had to overcome, some more obvious than others. The first one, which perhaps is not the most obvious one, was that during the construction of the MSE walls, we had to maintain traffic along Preston Street. And so this really limited the length of geogrid that we were able to place for some of the layers. And you can see that schematically on the right. And so obviously, because of this restriction, global stability and external stability were affected by that. And you can probably see them a little bit better here with the two photos that I have at the bottom, where traffic was maintained behind the fence or the Jersey barrier. And really, it limited how much space we had in terms of laying out our geogrid. The other technical challenge, which probably is a bit more obvious than the first one, were just the magnitudes of the loads and how close they were to the front face of the wall. If you recall, I mentioned that the shadow pressure underneath the SPMT was 105 kPa, and during its actual travel, it got as close as 0.8 meters to the front face of the wall. And so, as you can imagine, the combination of restrictions on the geogrid length and the magnitudes and the proximity of the load to the wall made external, internal, and global stabilities very critical. At the time, which was, I think it was last year, RSWall did not exist. And so we, at the time, used MSEW Plus for internal and external stabilities, and Slope W was used for the global stability. But after I'm done with these slides, Sina is going to show how the same analysis can actually be done in both RSWall and Slide 2. And so with that, here I'm showing the east wall just a few moments before the bridge was transported with the SPMT. And here's a picture of the west wall. And this is, or it was the moment of truth, really. And this is what it actually looked like when the SPMT was transporting the bridge. And you can already see very clearly how close the SPMT was to the front face of the wall. It's definitely not something you see every day, or at least it was for me. And so here I'm just showing a brief video of the SPMT as it's traveling. It's not the best view. I think the next video is probably going to show it a little bit more clearly, but that's just the general pace that the SPMT was traveling with. And this is probably a better video of just the scale of things and how close the SPMT towers were to the wall. So I don't know if the video did it much justice, but I think this picture probably does. And it just shows you the scale of things. You have the SPMT with the bridge jacked up on the hydraulic system and the lifting frame, and just how close the tires were to the wall. If I were to conclude this overall, just the selection of the MSE wall for this application, although it had its challenges, predominantly from the restrictions that we had and the magnitudes of the loads, the team was able to successfully execute it. And it was definitely the right choice in the end. And so with that, I will pass it back to Sina, and he will demonstrate how the analysis that we did could be replicated in RSWall and Slide 2.
So as Ali mentioned, it was a very interesting project. So now we want to take the project to the RSWall program and see how we can model the MSE wall in RSWall and then take it to Slide. So I'm going to open one RSWall software. At the beginning, when you open RSWall, you see this window, the welcome page, that you can pick the type of wall that you can model. Like the default is empty, but you can pick the type of wall, the type of standard that you want to analyze your model. I'll start with an empty project. Then in the project settings, you can pick the units, unit types, wall type, which for this case, it is segmental. Segmental includes the MSE walls and block walls. Design standards, we do AASHTO 2020. So we try to replicate whatever the project was originally. Failure modes, we have a sliding overturning bearing, which are external, and for internal, we have internal sliding, the crest toppling, and reinforcement failure modes. And for the methodology, for active pressure method, we do column method, and for tension reinforcement, simplified method. So these are the typical default of the program. Next step would be to define our wall unit. This one, to model the same wall, we do the wraparound wall type here, and with the dimension layer height of 0.45. Then in the profile section, we define the height of the wall, which was 1.8 meters with no setback. So this is the profile of the wall, and then we can add the wall using this profile. When I hit OK, the wall is added. So 1.8 meters of the height of the wall. This wall had a leveling pad as well. So we add the leveling pad with the dimension of 600, 2.8, and 300. And hit OK. So this is the leveling pad. And for the base strength, since it's MSE wall, we go soil on soil option, and we hit OK. So this is about the geometry of the wall. The next step would be to define the soil. Soil back slope and front face will be included in the soil part. Back slope would be horizontal, so no change in the back slope option. For the front face, it will be horizontal, but our embedment depth would be 0.3 meters. Keep in mind, I'm going to check this box to consider passive resistance of the front face as well to help the sliding at the base of the wall. The next step would be to define the soil properties. So we have the reinforced soil. The unit weight is 19, and the friction angle would be 34. Second soil type would be retained soil. Unit weight of 20, and the same friction angle and delta basically as we have in the program. Third one would be foundation, and the for foundation unit weight would be 19 and 34 for the friction angle. We're going to add one more material type, which is a leveling pad. And for this material, we're going to pick 23 for the unit weight, 35 for friction angle, and 200 for cohesion. So it's a very strong material. Hit OK. Now we assign the properties. So we pick from the left menu, and we assign to the right side. Retain would be the backfill, foundation, and for the front face and leveling pad, we will pick the property of the leveling pad and hit OK. So this is the soil assignment. The next step would be to define the loads that we had, and Ali mentioned the project. They had a horizontal distance of 0.8 from the wall that the load is applied. The magnitude is 105, and it is a permanent type of load. And then we assign it to the segment, and we hit OK. So you can define different loads, and if you have multiple segments in RSWall, you can assign different loads to different segments as well. Now we go and define the reinforcement properties. We change the name, and the reinforcement would be geogrid. The allowable tensile strength would be 56.8. For the pull-out calculation, the inter-sliding friction angle would be 25. We use coefficient of interaction and coefficient of interaction of 1. And for the connection, we use the same value of 56.8. So once I hit OK, the reinforcement is defined. The next step would be to define the layout of the reinforcement. So you can see how I follow the steps of different tabs and different menus. Everything is like in a right process. So we're gonna have 5 different reinforcement layers. I'm gonna pick the uniform for the layer, the length at the beginning, and I'm gonna pick 2.5. And for the elevation, I'm gonna do uniform and the value of 0.45. But this wasn't a uniform reinforcement arrangement. You saw that the top 2 layers, they were longer. So I'm gonna uncheck this option, and for these 2 layers, I'm gonna change them to 5.1. Also, the spacing of the top 2 layers, they were closer than the bottom one. So this one, I'm gonna change it to 1.65. And once I hit OK, the reinforcement arrangement would be something like this. So this is very similar to the project that Ali explained, the loading reinforcement arrangement. I'm going to save this model. It's ready to be computed. So I'm going to change the name to case study 1. And go to the results tab and click on compute. Factor of safety is 2.07, which satisfies the LRFD criteria, and it is for internal sliding of the reinforcements. You can always filter and have different options. For example, you can look at the base sliding, bearing, and overturning. As a test, for example, if I don't consider the effect of front face, the passive resistance of the front face, and hit OK, and I go back to the results, compute again. Now the failure is at the base sliding. Factor of safety is 2.5, and if you look at overturning, bearing, and base sliding, you can see that if we don't consider the effect of this front face and the passive resistance of the front face, the failure mode changes to base sliding compared to the previous case that was internal sliding of the geosynthetics. As I mentioned, RSWall has detailed hand calculations. So I open the report generator. In our report generator, you can look at project settings, soil properties, reinforcement properties. And in the results section, you can see all the calculations that we had to calculate the CDR and factor of safety. And all these numbers are going to the numbers coming from AASHTO, for example. These are article, for example, 11.3.1 from AASHTO. If we go to external, like summary, we have the summary of the CDRs, external forces, all the calculations, hand calculations are provided here. And this is the basis sliding, which is the most critical case. And you can see that how the resistance and driving forces are being calculated. Also, you can export it to a PDF file and look at the PDF data as well. After finishing the internal design, now to do the overall stability analysis, as I mentioned, RSWall is integrated directly to slide 2. So I click here, I pick the segment that I want to take to slide 2 and click open. And I'm gonna save this as case study 1, slide 2. And the model is being created here. So this is the model. A couple of properties have changed. So this is the model that we have in RSWall, and we brought it to slide 2. Let's look at the options, the default options here. The methods, Bishop, Yambu, you can pick any other method if you want. In terms of support properties, it is a direct integration. The values are the same as the values that are used in the slide in RSWall. And you can look at all of these. Also, the loading is the same as the loading that I had in the program, in the RSWall program. With automatically define the slope limits. I'm going to move a slope limit a little bit. I'm going to talk about this a little bit further after computing this model, because there are different options that you can consider. In terms of critical slip surface, it's a circular slip surface. We use auto-refined search method. So if I click on compute, it computes the model, and you can look at the failure surface. So this is the failure surface. Factor of safety is 2.4, and this is your critical slip surface. If you look at the original model, if you don't want your slip surface to go through this strong material, you can do something in addition to the previous step as well. So I'm going to duplicate this group, and in here, I'm going to change the dimensions a little bit. So I'm going to extend my model a little bit towards left. And the last part as well. And I'm going to add a layer of material here. And this one, I'm going to assign it the foundation material. And then I will move the slope limit a little bit to this side. So basically, I'm pushing the critical slip surface similar to the original design to go completely behind the reinforced zone and coming out here. So we can do that as well. So I'm going to recompute this model to see what happens. So this is the case number 1. So basically, the failure surface went through this strong material, and this is case 2, which the slip surface went behind the reinforced zone, completely overall stability and coming out of here. So factor of safety is 1.8. It is still good to go for the design purposes, but factor of safety is slightly lower than the original case. So with that, I'm going to pass back the presentation to Ali.
Well, thank you very much, Sina. So the second case study I'll be presenting on is a lock block wall. And the reason I'm choosing it is it was used as an alternative, more cost-efficient option to support the backslope behind the secant wall. This case study is not as exciting as the MSE wall with the SPMT, but what I'm hoping to demonstrate is that with proper risk mitigation measures and monitoring, more cost-efficient retaining wall options can be used. This was part of the Ottawa LRT Stage 2 Confederation Line project, which extended the existing LRT line further east and further west, which are shown by the red thick lines. And just overall, the project consisted of 27 kilometers of new rail, 16 new stations, and 34 new structures. Part of the 27 kilometers of rail were cut-and cover tunnel sections, one of them being what was called the Parkway Tunnel, which is going to be the focus over here. Excavation for this tunnel was a maximum of 13 meters deep, and many different types of supportive excavations were used along this alignment, including soldier pile and timber lagging, secant walls, lock block walls over vertical rock cuts, all sorts of supports, including struts, tiebacks, you name it. Essentially, any type of supportive excavation was probably used on this project. The section that I'm showing here is within the deeper part of the cut and cover alignment, where on the south side, we have approximately 13 meters of excavation that was required, compared to approximately 8.5 on the north side. And the type of shoring wall that was ultimately used here was a secant wall with tieback supports. Very briefly, because it ties into the context of the lock block wall, the geotechnical conditions here generally consisted of fill, which is shown by the gray material, on top of over-consolidated weathered clay crust, which is the dark green material, over sensitive Champlain or Leda clay. For those of you who may be familiar with it, it tends to have a sensitivity ratio of approximately 10, over glacial till, which is shown by the orange and the yellow, over bedrock, which is the purple material. And so going back to the excavation, there was approximately a 4.5 meter elevation difference between the south side and the north side. And you can probably see it a bit more clearly in this picture, where on the right side you can see the top of the beams for the secant wall compared to the left, which is showing the higher grade. And this is probably a little bit more foreshadowing. You can already see the soil nail wall and the lock block wall that was used on the south side. So the objective that we had here was to retain the backslope behind the secant wall on the south side. And you're probably thinking, why can't we just extend the top of the wall a little bit? But what is actually not shown here is that this higher section is over a limited length. And so in order to get your drill rig all the way up there, you would have had to backfill a much larger area, which was just impractical and not the most cost-efficient option. In addition to the fact that just extending the wall higher was not the most economical solution. And so the original plan that was chosen here was to use a top-down construction approach, which consists of soil nail walls. And I'm showing that in the profile view below. But the design was later refined and optimized to replace close to half of the wall with lock block walls with a bit of a backslope. And this is what it ultimately looked like after it was constructed. You can already see on the right side, you have your soil nail wall, and then tying into that is the lock block wall with a bit of a backslope. And so for the height that needed to be supported, which was approximately 2.4 meters tall, we had two options consisting of either 2 blocks or 3 blocks high with a bit of a backslope, depending on the option. And like I mentioned, at this location, the sensitive Champlain or Leda clay was actually quite shallow and was directly underneath the lock block wall. And so for that, we had to sub-excavate some of the material and replace it with well-graded, compacted granular material. And in addition to that, we rotated the bottom blocks, both of which improved the bearing stability of the wall. And lastly, there were no surcharge loads permitted behind the wall, not because the wall was not capable of it, there really wasn't any room for there to be anything behind it. And so normally when you're looking at gravity type walls, you're concerned with, in most cases, external stability, and in some cases you're interested as well in internal type failure. But looking at external stability mechanisms, you have bearing capacity, you have sliding along the base, you have overturning of the structure, and you have global type failure. I didn't probably mention it, but the lock block walls that were used here, they had interlocking shear keys, which really held the blocks together like Legos. And so for the most part, we were predominantly concerned with external stability as opposed to internal modes of failure. We did not expect the blocks to, for example, slide along each other, because that would imply that you're shearing through concrete, which with the height of the wall and the types of loads that were behind it is not plausible. At the time when we were doing the design of this, we did a bunch of hand calculations to demonstrate that bearing, sliding, and overturning were acceptable. And we did global stability and supplementary sliding checks in slope W. But again, similar to the previous example, Sina is going to demonstrate how design of these types of block walls can be analyzed in both RSWall and global stability in slide 2. And so generally here, the construction sequence, it consisted of building the soil nail wall, progressing towards the location of the lock block wall. And once you were at the location of the lock block wall, then construction of that began. Like I mentioned very early on in the presentation, typically gravity type walls, they use a bottom-up construction approach. But because of the limited space that was available here due to the right-of-way being close, we had to use a more top-down approach where we locally excavated small trenches and placed the blocks in front of them or inside the trenches and backfilled behind them with self-compacting material. which is not usually the more common way of building these walls. And once both walls were completed, the secant wall was then installed in front of it. And in this case, the clearance between the secant wall and the soil nail wall or the lock block wall was 0.5 meter. Now, the key thing here that made the design a bit more interesting were just the risks that we expected. The key one being the potential for remolding of the sensitive clay that was underneath the wall. Like I mentioned, we built the lock block wall first, and then we came in to drill the secant wall. So the operation of drilling the secant wall could potentially remold the soil underneath the wall and potentially compromise it, whether it's in a bearing type failure or over-toppling type failure. And so we had to place mitigation measures and monitoring approaches just to make sure the design was safe and the operation was acceptable. The first one and the most important one was preventing any personnel from approaching the wall during the secant wall construction. And if personnel had to approach the wall for whatever reason, full inspection of the wall had to be performed by a competent individual. And on top of all of that, we requested or required daily survey monitoring of the wall. We had many points along the top and bottom blocks of the wall, and I believe it was spaced at around 1.5 meters to 2 meters. And lastly, we were anticipating that there could potentially be quite a bit of movement that would not have been acceptable. And so in the end, if required, we would have reinstated the blocks. And in this case, we actually observed 11 millimeters of vertical movement after the secant wall construction was completed, and approximately 8 millimeters of horizontal movement. And so some parts of the wall were in fact removed and rebuilt after the foundation of the wall was rebuilt. And so, although there were risks identified with this type of wall, we were able to demonstrate that proper mitigation methods it performed quite well, as opposed to the more cost inefficient solution of a soil nail wall, which would not have potentially experienced the same types of concerns that we had for the lock block gravity wall. And so with that, I'm going to pass it back to Sina, and he will demonstrate how modeling of this wall can be done in RSWall and SlopeW.
Thank you, Ali. It was a nice case study. So I'm gonna create the second case study in RSWall. So it's the lock block wall, and let's see how we can do it in RSWall. So I'm gonna start with an empty project. In the design standard part, we are only interested in the serviceability for this wall. So I'm going to just pick the serviceability option. And also, as Ali explained, we are not interested in the internal stability of the wall. We are only interested in the external stability of this block wall. So with that, I hit OK. Next step would be to create the wall units, which are the blocks. So in RSWall, you can define like modular block. In the previous example, I did wraparound. This one, you can do modular block. As I mentioned, we have manufacturer libraries for blocks. I'm going to show you in another example the manufacturer libraries. But for this example, I'm going to name the first block a regular block, the first type, and the dimensions would be 0.61, 0.61, 1.22, 0.305, and 23.5, and with the constant shear of 50. And the second one is going to be rotated block. And this one, the dimensions would be 0.61, the rotated version, 1.22, 0.61, 0.61, and 23.5. So we have two different types of blocks. Then we go to the profile. In the profile section, You can have uniform blocks, similar to the previous example, or a non-uniform block. So for the non-uniform block, we change the block one to a rotated block and the top two ones to the regular block. So I'm gonna hit OK. And then by clicking add wall, the wall is being created. So for this example, we have leveling pad as well, similar to the previous one. It's going to be 600, 1.72, and 500. This is the leveling pad. And for the base strength, this one, since it's a lock block wall, it is precast on sand. So we keep it as is. Then we go to the next part, which is to define the back slope topography. For this example, we do the broken back slope. Initial run of 0, a slope run of 0.915, and the slope height of 0.61. When I hit OK, the back slope topography is being created. For the front face, we don't consider any front face for this wall. So when I put 0, it's going to be flat, no front face. Then we define the soil properties, unit weight for the soil one. Let's call it compacted granular material. So unit weight is 22, friction angle is 36, and soil structure friction angle will be 25. The second one would be Lida clay. Unit weight of 16.5 and the same friction angle and soil structure friction angle. We add a cohesion of 6 for the foundation. When we hit OK, now we can assign the properties. Already the compacted granular material is assigned. We do the clay for the foundation and we hit OK. So that's how your geometry looks like. Let's save this model. There was no load in this project, so I just keep it as is. And let's compute. So it's a simpler model. Factor of safety or CDR is 2.01. You can see that we only have a couple of external options since there is no reinforcement, and we turn off the internal failure mode. And basically the pad sliding and the base sliding are the more critical failure surfaces. We take this model to slide 2. We open the model in a slide. So this is the model in a slide. And you can see that the slope limits are created like this, and the foundation material are generated. Keep in mind, I always say that in every webinar that if you want to model the block for block walls or MSE walls, do not use the infinite material. You can see that the default that we bring is the very high cohesion and very high friction angle instead of having an infinite material for these blocks. So again, we use same methods, and we use the circular method since the original design was the circular analysis. And you can just compute. You don't need to do anything. You can just compute. So instead of having hand calculation, take your model to another program, recreate it again. RSWall and slide helps you with doing internal and overall design very quickly. And you can see that the overall factor of safety is 1.75, which satisfies the overall failure. So this is the overall failure mechanism. I wanted to show you another example of the RSWall program related to block walls. So as I mentioned, we have manufacturer libraries, and this is one of our verifications. In the current release, we have manufacturer libraries only for Ready Rock and Magnostone, but the next version, which will come in the next 2-3 weeks, It has a lot more manufacturer libraries in addition to these two. For the sake of this example, I picked different blocks from ReadyRock, and the profile would be a non-uniform profile. You can see that for every layer, we use a different block. And we had a set at the batter angle of 5 degrees for these blocks as well. And it looks like this. And we had a leveling pad as well. And the CDR is 1.45. So this is another way of creating the block walls. Same model, took it to a slide software. So you can see these blocks are created exactly the same in the slide software. And if you look at the overall failure mode, for this example, I use non-circular failure mode. Sometimes block walls or ABM walls, you should use non-circular failure mechanism. And you can see that factor of safety is 1.29. And this is the non-circular failure surface. To move on with our presentation, there is just one part that I wanted to mention here, which was this is a new feature that we released in a slide 3 days ago. It's called tension map, and the application is mostly to be used with the RSWall software. It's basically it's a procedure accepted by AASHTO, which determines the maximum tensile force experienced by geosynthetics during a limit equilibrium analysis. It's a new method. It is now available in the slide if you use slide software. And then these results can be transferred to RSWall in the new release that we have, new update that we're going to have in the next couple of weeks. This will be integrated into RSWall. Basically, you can take this maximum tension and optimize your reinforcement design in the RSWall program. And it will look like this. Basically, this is the original design. Factor of safety is 1.2. But when you bring the tension map from a slide into RSWall, so it's going to be the other way of bringing the tension map from a slide to RSWall, factor of safety drop to 0.6. So considering the maximum tension experience in the reinforcement will change your support arrangement and optimization of your supports. So that's the feature that will be available in RSWall. And now currently the slide version is available. So thank you, everybody. Thanks, Ali, and for collaborating with us from QIT and the QIT technical team. I hope to see you guys very soon in our fourth webinar series of RSWall. Have a good day.